mechanical IQ. Today's topic is limitation of using forces to represent a mass in FEA. My name is Marwan Azzam. I'm a technical support specialist, and with me here today is Dave May, a technical specialist with Autodesk. Welcome everyone, and let's get started. Just a couple of things here before we get into our topic of the day. I just want to go through a few of the recently added simulation mechanical support knowledge base articles for July. I'll just go through a couple of topics here that are listed. Few of these analysis fails when running from network driven simulation mechanical. How to map thermal results from simulation CFD to simulation mechanical. Importing a third-party mesh in Autodesk simulation mechanical, and so on. I do encourage everyone to go to that knowledge at autodesk.com website that is listed here to get, there's a lot of articles being added every day dealing with different topics. So it's a very good resource to go to if you have a question that might already be answered with a lot of detail in those articles. Like I said, we add those every day. This slide deck will be available to download, and you will get that link inside of it as well.
So let's talk about kind of what we're talking about here and why we would care, right? So in this case, here's our problem. We have a motor riser, and we need to analyze it against static loading and modal, or natural frequency. So we have a certain few operating frequencies we really need to keep our, out of our range, and we have some certain amount of load that we need this thing to just be able to carry, right? In this case, we have a 2,000-pound motor, and it's mounting to the kind of the corner pads on the top of the frame. And we do have kind of a location for that center of mass too. So really, how are we going to represent this, right? And there are kind of a couple ways we could do that. A really simple way would be a force, right? We can just apply a force to those pads. A lot of times that's what people do to represent things in a linear stress type environment. You just add a force to represent something that's not there.
And in fact, you can use a remote force too. You don't even have to have elements connecting to those pads.
Yeah, that's absolutely right. So you could do remote force in the central location, like connected to where that centroid would be, whether connected through elements or just a remote load.
Yeah, and this way, the idea here is you don't want to you don't want to model the motor itself. You don't care about the motor, you don't care about the connections that the motor has to the frame, you just want to represent that load on the frame. And that's why you would use that force.
Right. Now, that works for some situations, but not all. So another option, and that's going to kind of work for the rest of our things here, it would be using a weight or a lumped mass. And why we want to do this is going to kind of become very apparent as we go through some different types of analyses specifically. But really using a weight that in conjunction with a gravity load or a centrifugal load, something like that, will give us effectively the same type of thing as a force could give us if we applied it properly. Now, we'll see as we get through this a little bit that a weight is not always the same as a force, and there are times where a weight or mass represents something that a force just can't ever represent, especially when you get into mode shapes and frequency type analysis.
Yeah, so if you're just doing a linear stress analysis, a force would actually be a little simpler and easier to use, and there's no reason why you shouldn't be using it. But once you get into the modal, the vibration type of analysis, you're going to see that you really don't want to be using a force.
Yeah.
So what is a nodal weight? A nodal weight or lumped mass is a load that can be applied to a node in most linear and nonlinear structural analyses. It is used to represent the mass of an attached part or subassembly that is not included in the actual model geometry. So that's the whole idea. You don't want to represent the actual part or assembly. You just want to have the effect of that part or assembly on your model of interest. A nodal weight can be used to resist the translation or rotation of a node. in order to resist rotation, the nodal weight must be attached to an element that supports rotational degrees of freedom, such as beams, plates, or shelves. For elements with 5 degrees of freedom, such as plate, with lack of rotation degree of freedom but the normal to the element, a nodal weight will only effectively provide rotation resistance about the other two axes. So basically what this is saying that for rotation, you have to pay attention to the rotational degrees of freedom and what elements support rotational degrees of freedom. That's in a nutshell what it's saying. A nodal weight is equally effective in all transition directions, uniform, or it can have different effects in each direction. So when you define a nodal weight, you have the option to keep the uniform box checked, in which case it will have the same effects in all 3 directions. Or if you uncheck that, you can have different weights having an effect in the different directions, X, Y, and Z. It's user's choice. If the nodal weight is to be effective in the rotational directions, you have to specify the appropriate values of the mass, moment of inertia in the X, Y, and Z directions. Typically, these would be different in the X, Y, and Z directions for the mass, moment of inertia, unless you have a sphere or a perfectly rectangular cube. You can have 3 different values in the 3 different directions. And there is a lot of more information. If you go to the documentation, it has a lot of detail on what analysis types and how to use the nodal weights and nodal moment of inertia. Next, we have our example model that we're going to go through. This is the structure or the frame that the motor is going to be attached to. We have a few design scenarios where we're going to go through and show the different results and the different way of setting it up. So I'm going to exit the presentation here and actually go to our simulation mechanical. Here we have the model already open. It is already meshed. And we have fully fixed constraints applied to the bolt holes at the bottom plate here, as you can see. And we're not going to, so we went through the steps of doing that. Next, we want to, so this first load case is going to be linear static stress, and we're going to represent the weight of the motor with a nodal force. Again, there's a couple of ways. We can just select those pads and apply a remote force. I'm not going to do it that way just for the sake of comparison. What I'm going to do first is I'm going to select those surfaces, 4 surfaces that I want to apply the load to, and go to draw and create the centroid. This is under draw, centroid creator. We have the 4 surfaces here, and what I want to do actually is I want to connect the centroid to the geometry with quote-unquote spokes, or it could be just, and these would be part, let's say, 20. And what this does, it creates all these lines from each node on those surfaces to the actual centroid of those 4 surfaces, which happens to be, in this case, right in the middle. But we're going to make this a bit more interesting. We're going to say the center of that motor, or the motor assembly, is not really at the center. It's offset 12 inches in the Y and Z directions. So what I'm going to do here, and still in draw, I'm going to select this vertex here. And I'm sorry, I'm going to click on, what is that? I needed to do a move point. And I want it to move 12 inches and 12 inches. I'm going to use relative. And here it is. So I just move that centroid, not move the centroid, move the point to where I want to apply the force. So this first case is I'm going to select this vertex and add just my nodal force representing the weight, which is 2,000 pounds I can actually put minus 2,000 pounds here in the y direction. And that's basically going to represent the weight of the motor. And we just go to analysis and run simulation. By the way, this part here is going to be rigid elements. The new part that I created for all these lines. And let's look at the results. I already ran this analysis, and these are the displacements we get. 8.7 e to the minus 4 inches is the displacement, and of course you get some stresses associated with that. So that is the first way of doing this. Second way of doing it would be, if we copy this design scenario, would be using nodal mass. So I'm going to select my nodal force, delete it. And by the way, when we define a nodal force, we define which load case it goes into. And in this case, it went to load case 1 by default. When I add nodal weight, and it's going to be in, you have the option, either units of force or units of mass. In this case, we'll keep it as units of force, and we're going to say 2,000 pounds uniform. There's no load case multiplier here or load case indicator. This is done in the analysis parameters. When I go to analysis parameters, this nodal mass will follow the gravity multiplier. Okay, so if my gravity multiplier here is 1, and the direction that's going to be effective in is also defined in the gravity direction. In this case, of course, it's going to be minus 1 in the y direction. So that's going to be equivalent to my force. And if I wanted to represent something like at that same node, something like a nodal moment of inertia, I can also do that. Oops, no, not nodal weight. That's going to be, actually it is here. I can also specify another load, which would be, I'm just going to make up numbers here. I'm going to make them uniform, 100 pound force per inch squared. That's my moment. And in order for that to be effective, let's make a load case here, some angular acceleration. That multiplier, either the omega or alpha multiplier, has to be non-zero. And on the centrifugal, maybe I'll have some kind of angular acceleration value here. So right now, but we're going to concentrate more on the nodal force. So if I run the simulation and look at the results, that's my design scenario 2. This should give us the same, of course, stress and displacement as the nodal force. So we represented the weight of the motor in 2 ways. First design scenario was a force, second design scenario was a nodal mass. And if you quickly go to design scenario 2, where we have the moment of inertia, of course we can see that we got some displacements and we get associated stresses. In case this thing was to jerk or tilt for some reason, that nodal moment of inertia will give you the effects of that motion.
So it's important to note that, you know, for just a basic linear stress, we saw pretty much identical results as far as displacements and stresses go from using a force versus using a mass with gravity.
That's correct, yeah. So you apply the mass, and in order for that mass to give you any effect, you would have to have the gravitational multiplier and gravity defined. Next, we're going to do modal analysis to calculate the natural frequencies. So if we go and change the analysis type to linear modal, natural frequency model. Yes, you want to create a new design scenario. And in this case, I actually don't want any effects, no nodal mass or moment of inertia. And by the way, when you switch over to a modal natural frequency analysis, and you select a node, you actually cannot add a nodal force. But by the way, in previous versions of the software, you could. So if you, I'm not sure which version that change happened, but previously you could actually apply a force, and unknowingly that force actually doesn't do anything for you. Yeah. It has no effect.
Yeah, it was just thrown out by the solver. Effectively, the setup was the same between a natural frequency and a modal with load stiffening, which actually does use those forces. Mm-hmm. So the setup was identical, but the solver just would ignore them.
That's right.
You kind of had to know what you were doing.
Yeah, but this latest version here, it doesn't actually at all allow you to define a force on the model. So just to see what the natural frequencies, and by the way, those rigid elements will have an effect on the natural frequency of the model, in case you are wondering. They will stiffen it because they are connecting those 4 pads rigidly, which is probably not a deviation, much of a deviation from real life. If you have a motor assembly sitting on those pads, that's going to be pretty stiff as well. So if we go and load the results of the modal analysis here, and we're not running the model live just for the sake of time. Let's take a look at the first 5 natural frequencies, which is what it calculates by default, the first 5. So the first one is about 54.62. 145. 162.78, 166.6, and the last one is 175. So these are the first 5 natural frequencies. There's no weight, no load, nothing, just the structure itself here. Now to the next design scenario, which really is not what you want to do. Let's say someone said, well, I have the weight of the motor and I do want to represent it with a force. I can't do that with a natural frequency. I'm going to change this to natural frequency with load stiffening because that's what allows me to actually add the force to my model. So I'm going to go ahead and do that. I'm going to switch over to natural frequency with modal stiffening. And by the way, you have to change the element type from rigid to beam. Beam elements will not work here, but that's fine. What you do is you make stiff beams. Let's say round cross section of 3 inches. And for those beams that are going to be quite heavy now, for those not to have much of an effect except for the stiffness, you would go and edit the material and make the density equal to 0. This way they don't contribute any weight to your model. Otherwise that weight will throw you off quite a bit.
Yeah, and again, the reason we want to get rid of that weight is we're already basically considering the entire weight of the motor and attachment points with the loads we're applying here.
Yeah, which is going to be,
which in this case is going to be wrong.
Yeah, going to be that minus 2,000 pounds in the y direction. And one last thing here before we run the analysis is you want to go to analysis parameters, and for the sake of uniformity, I don't want any acceleration multiplier. I don't want to consider my gravity. You can see the gravity load here. I don't want that, so I change the acceleration multiplier to 0. And it's gone. So right now we have, like Dave said, the wrong way of doing it, which is representing the weight of the motor with a force. For that, we had to go to a load stiffening analysis type. Now, if we run this model, which we've done, and look at the results, which is this load case here. Now, of course, due to the compressive load, the compressive effect of this load, it's not so much stiffening, it's actually loosening. You're getting little lower frequencies here. We're getting 51.7 and instead of 54. You had 160 something, you got or 140 something, and so on. So someone might look at that and say, okay, well, that's what the weight of the motor is doing for my frequencies. And actually, that is wrong. What you really want to do is you want to change this modal, this analysis plot to just modal. So that's going to be our load case number 5. It's going to be modal, and you notice that our force disappeared because modal doesn't support the force. I'm going to select this and add a nodal weight of 2,000 pounds. And run the simulation. And when we do that, let's take a look.
So this, just to kind of point out this little effect, this particular version where we have the mass attributed to that location, but we don't have a force and we aren't looking at load stiffening, it's throwing out all the load stiffening effects, right? It's looking only at how much the mode shapes change when we add a mass of that much at that location.
That's true. That's true. Now, load stiffening also does allow you to add a nodal weight. So if that indeed is what you were looking for, you do have some loads that will contribute to the stiffening, or then you could do that. You can use the natural frequency with load stiffening. But for the sake of our example here, that's not what we're looking for. We're just looking for the effect that this motor will have on the natural frequency. And just by looking at the first natural frequency here, that comes out to be 19.67, we actually see a huge difference. Actually, I have a table here that shows the different results of the different design scenarios. So my first design scenario 1 and 2, the first two design scenarios were linear static stress. And we're representing in design scenario 1 the weight of the motor by a nodal force. And in design scenario 2, we're representing the weight of the motor with a nodal mass. And the deflections are identical, and they would, of course, result in identical stresses. So in that case, it's okay to use one or the other. However, if you are doing any frequency type analysis, you don't want to use the force load to represent the weight of the motor. So my design scenario 3, I can look at my first 5 natural frequencies: 54.62, 145, 162.8, 166.6, and 175.22. Design scenario 4, which is the wrong way of doing it, with nodal force, the natural frequencies dropped a little bit from 54.62 to 51.71, and so on. In this case, this is about
I think at most it's about a 5% drop. So the first mode is the one that is affected the largest amount, and it's about 5% change.
Yeah,
whereas the difference between the original modal analysis and the one including the mass is it's off by over 100% compared to the correct answers of including the mass. So it's really very significant to include the mass versus the amount of change due to load stiffening is minor, very minor. So again, arguably you could do a natural frequency with load stiffening analysis and include the mass and gravity to represent that. And then yes, you get both the mass effects and the force of the small amount of force effect included there. But to Marwan's point earlier, that change due to including the force is so minor compared to the mass that you almost don't care most of the time.
That's true. That's true. Again, we wanted to show you the difference between that, and once you know what the mass does and what the force does, then you can make a decision, which one will suit your analysis better. But it's very important to know that they are not interchangeable in all cases, and you do want to be careful, especially when you're doing a frequency type analysis, that the forces will probably not give you what you are looking for. The other thing that maybe in the linear static stress that you want to use mass instead of a force is if you had multiple forces thrown about the model and you wanted to change them, you'd have to go and change each one individually, whereas if you are using a mass, if you just change the gravitational acceleration or the multiplier, then that affects all of them in the same time. That's just one example. We're not going to go through all possible combinations of why one would be easier than the other.
Yeah, I think a good easy rule of thumb is that anytime you're getting into dynamics, you need to start considering mass, right? Whether it's vibration, like a natural frequency analysis, if you do seismic type events, mass is very important there too. And into nonlinear, right? Nonlinear static doesn't really matter, but nonlinear dynamics, like a mechanical event simulation or MES analysis, mass means a lot there, right? That's true. Everything has inertia. So let's say two things colliding together. If the mass is off, the way those things react is going to be completely different.
Yeah, the force is not going to give you what you want there. That's for sure. Yeah. Yeah, I think that brings us to the end of our presentation here. Thank everyone for watching this, and we look forward to providing more of these webinars. Thank you.